So today we will study Maxwell's second equation. What is Maxwell's second equation? Suppose there is an electric field in this direction and I am considering a closed loop like this. This is a point A and this is a point B. A charge Q is taken from A to B in this way. Then the potential across A to B, potential A to B V is equal to minus E dot dl dot dl. Okay. E is electric field and dl is the length, small length across this closed loop. Suppose this is the center and the position vector of A point is RA and position vector of B point is RB. Okay, so potential from A to B is equal to minus E dot dl. This minus is due to the fact that work is to be done to move the charge from point A to point B. Okay, now according to Maxwell's second equation, if this is a closed loop, that is for closed loop, V is equal to closed loop E dot dl is equal to 0. Potential for a closed loop, potential is equal to E dot dl, potential for closed loop is equal to 0. Here also A to B. V is equal to E dot dl. Okay. Now potential for a closed loop is equal to 0. Okay. Suppose length L. So the net result is closed loop E dot dl is equal to 0. Potential across a closed loop is equal to 0. Now this is the integral form of the Maxwell equation. To get the point form of the Maxwell equation, what we will do, we will apply Stokes theorem. Stokes theorem. Now what is Stokes theorem? This is a very important theorem. It converts a line integral into surface integral. This line integral E dot dl can be converted into surface integral curl of E dot ds. Okay, so we can replace this. So what we will get, del cross E is equal to, of course this is a vector. Okay, so del cross E is equal to 0. This is the point form of the Maxwell equation and this is the integral form of the Maxwell equation. This is the point form or differential form of the Maxwell equation, and this is the integral form of the Maxwell equation. So Maxwell's second equation states that the potential difference of a closed loop is equal to 0, or work done to take a charge from a point A to B, again B to A, is equal to 0. This shows the conservative nature of electric field. Conservative nature of electric field. This tells us the conservative nature of the electric field. That is, that in an electric field, if you move a charge from a point A to a point B, work is to be done. But if you move a charge from A to B, again B to A, that is, you reach at the same point again, then no work is to be done.